Okay. So the last talk of our morning session.
Really last?
Morning.
Morning session. Okay.
Will be by Yuri Berest from Cornell, and Yuri, if it's the same as in the program, will be talking about Hodge decompositions and derived Poisson structures in rational homotopy theory.
Okay, so first of all, I would like to thank the organizers, Ted Voronov, Katya Shimakova, and Alexander Odesky. I guess this is the last in-person talk. Is this correct? Maybe it's time to get up and thank the organizers for this remarkable conference. They really made it happen. So. Okay. So, well. My talk will be in some sense old-fashioned. I will try to apply algebra to topology. I will start with a topological part, and which to some people is probably very familiar. This is the subject of string topology. Yes, so I should probably say that this is based on joint work with Ajay Ramados, who is at Indiana University, and Yinin Zhen. He's now postdoc at Colorado. So maybe the main reference, there are several papers I will be referring to. The main reference, it's a paper which just appeared, so it's called Hodge, decomposition of string topology. So I think it's a for mass sigma. Well, I should say it's it was a rather strange experience after we submitted this paper and received actually 2 referee reports. Referee pointed out that the problems that the problems that we solved actually well, received a good deal of attention, which we didn't notice. So it actually well, I don't want to say some kind of famous problem, but a very natural problem. So there were several conjectures, and it turned out that, well, we proved one of these conjectures, but under very natural but different conditions. Okay, so let me say a few words first about string topology, and later I will be translating this translating to the language of non-commutative geometry. In particular, I should say my talk will have connection to the talk of Alexander Odesky, in the sense that I will be using non-commutative Poisson structures, but the derived ones. And I will try actually to define what exactly do we mean by derived Poisson structures. We actually sort of studied them algebraically some time ago, but I think because of this connection, it should be taken more seriously. So it has a real topological application. So it probably more interesting than we originally thought, I should confess. Okay, so let me take one simply connected closed oriented d-dimensional manifold. So the main actor on topological side is a so-called free loop space. This is just the space of all continuous maps from the circle to X, equipped with usual compact open topology. So such maps, I will be thinking of a circle just sitting inside of complex numbers. So such maps, points in this space are just continuous maps. And I will be thinking of the circle as being unit complex numbers. Oh, sorry, what happened?
Do you have a question?
Sorry, is any questions? Are there any questions? Okay. I got scared. Okay, so I should notice that this space has a natural S1 action. So circle naturally acts on this space just by rotation of loops. And what we can do, we can look at, well, first of all, we can look at usual homology, which is always taken with rational coefficient. And we can look also at S1 equivariant homology, which is the homology of just Borel construction for this natural S1 action, again with rational coefficients. So sorry, what?
What is ES1?
ES1 is a universal bundle over S1. So we are, yeah, so it's a contractible S1 space, right? Well, okay, there are several models, explicit models for classifying spaces and. Sorry, what? S infinity, or if you wish, infinite. There is a remarkable. Okay, it's a different subject. I don't want to start it. There is a remarkable construction, classical, due to well, for any topological group, due to Milnor, that is infinite join of copies of topological group. When you join groups together, you kill higher homotopy groups. In the end, you will get a space which is contractible, but it carries naturally diagonal G action. And this is a famous Milnor model. But there are many others, well, depending on generality of work. Okay, so right, so Chas and Sullivan introduced I think the preprint first appeared in '99. So they introduced certain family of operations on homology and S1 equivariant homology, which go under the name of string operations, which were defined originally in geometric way, except that, well, as I will try to explain, except that there were some intrinsic problems with transversality. So sometime later, several groups of people try to redefine these operations in homotopy, in algebraic way or homotopy theoretic way. I will mention some works. And this what initiated the subject of string topology. So for me, there will be sort of two important, probably most important operations. One is usually denoted by black circle called loop product. And I will define it vaguely following the original definition of Sullivan, Chas-Sullivan. And another remarkable operation. So loop product is actually, maybe I should introduce some notation, but I'm thinking if I will be using it. So let me introduce some notation. I will denote by H sort of doubled shift, just shifted homology of Lx, shifted by dimension like this. Maybe reduced homology. And what Chas-Sullivan did, they defined this loop product on this shifted homology. Well, making it a commutative graded algebra. In fact, later, I think Felix Halperin and other people showed that this is actually a BV algebra. I will not go into that direction, but what is important in terms of this loop product, you can define another structure which is called string topology bracket. So this is, well, this is actually a Lie bracket, graded Lie bracket on the reduced S1 equarian homology of this free loop space. So this is what is called string bracket or string topology bracket. So it is, well, oh, sorry, I will not write anything more. I will move here. So, right, so let me roughly so I will actually later give an explicit and precise formula for this bracket in terms of in more algebraic terms, but just to give an idea how originally these operations were defined, loop product and string bracket. So loop product is, roughly speaking, is, well, combination of two operations, intersection product and natural composition of loops. So I just define it in some way. It will be not precise definition for because of assumptions that I will make, and this is exactly what makes it hard to define. It's a big subject, and I am not expert on it, and I don't want to go very deep into this. But just to give you impression, this is actually a geometric operation, and the theorem that we will prove is entirely geometric. But we don't know geometric proof of this theorem. The proof will be by careful translation into sort of more algebraic world. So maybe it's a good exercise to see from purely geometric point of view whether you can prove the theorems that I will state. Okay, so well, let me first of all introduce. There is a natural operation, a natural map from Lx to x, which simply evaluates a loop at a certain point, say at 1. You can take two, well, cycles, let's say HP in Lx and beta in HQ, I will think of these cycles as simply singular chains. So I will be representing them by maps like this. I'm more or less faithfully following Chas and Sullivan. And then I will consider, yeah. So now the key assumption is the following. I can compose, let me write maybe a commutative diagram and make this assumption. So I can compose these chains with evaluation map. So I will write it like this. Maybe I need a notation. Now I have a natural diagonal map. And I can take a pullback like this. And I assume, so, well, this loop product will be defined under assumptions that, well, so the image of this map is transversal to the diagonal, right? Transversality assumption. That's the main problem to make this things algebraic. But once you have it, well, you can define, well, so first of all, for any, say, S and T in E, we have alpha S beta T living inside of fiber product through this evaluation map. So what I get actually a map. I'm thinking of E as sitting in. Yeah. Okay. Let me finish and then explain. Again, maybe I shouldn't write these formulas because I'm not using it, and I will. But just to give you an impression, what kind of things are involved. So this gives you a map from E to this fiber product through the evaluation maps. And then what you can do define this this loop product. You can compose this map with usual composition of loops, or with a map induced by composition of loops from fiber product to LX. So you have one map which is like this. This map psi with a shift by degree. And then the map induced by this natural composition of loops. And this lands in, doesn't shift the degree. So that was original definition of the loop product. The point is that, well, so probably the theorem is that there is a natural product that for chain satisfying this assumption is given by this formula. So I should say that Cohen and I think Jones actually clarified this, gave a homotopy theoretic construction that has no any deficiencies. And later there was a construction of Felix and Thomas, which is also very nice. This I can say more, that what we actually using, so gave sort of algebraic construction, but I should explain what algebraic here means. But now once you have this loop product, the bracket is defined as follows. So now I can be very precise. Once you have a loop product, the bracket is defined as follows. So yeah, maybe I introduce. So when we have an S1 action on this free loop space, we have a natural Borel vibration for Lx. And what you can do, of course, you can look, well, let me denote this map pi, and I will probably need for later use. So let me define reduced S1 equivariant homology of Lx simply to be the kernel of this map. It's just a composition looks, it's exactly, huh?
Is it just standard product in P1 or something different?
No, it's a composition of loop by reparametrizing loops, just like you compose loops in omega x in base loop space. Right? But anyway, don't worry about this. I will give a different, as I said, so there is a whole this. I think this paper this paper was never published, so it's only exists as a preprint, and maybe I'm wrong. Maybe it was published later, but I think it's not published. It exists only in preprint, but it kind of induced this, well, motivated the whole area, and different construction, quite nice, have been done. I will define what I'm actually using carefully later. Okay, so right. So what I mean by equivariant, sorry, by equivariant S1 equivariant homology is just the map induced by pi in this Borel vibration and its kernel. So that's definition. And if you look at Serre spectral sequence associated to this vibration, or probably rather induced vibration, if you shift everything to the right, take omega omega bs1, which is S1, right? And if you look at the homotopy vibration sequence, so this I will denote. So homotopy orbit simply LXHS1. So this is a notation I will be using to shorten. So if you look at this vibration sequence, homotopy vibration sequence, and look at the Lyrae spectral sequence, or Lyrae Serre spectral sequence, it's actually degenerates, very well known. It's and it produces you what is called Gisin sequence, non-exact sequence. So this is all very well known, especially for people working in cyclic homology, of the following form. Again, I will refer to this later, coming from Serre spectral sequence. Well, I was just teaching this in my homological algebra class. So I will use a notation, somewhat strange notation, but it's this notation will be explained later, or people who actually know cyclic theory, cyclic homology theory well immediately see what it is. Sorry, I should write n minus 2 S1 Lx and so on, BAS. So, well, right, it's so I should denote it by G, but this is just the Gisin map, also known as Kohn periodicity map. Well, so this this is a map simply induced by canonical projection. Right, and this is well, map which I call con differential. And then to define string bracket, I will simply do the following. So string bracket sorry, is defined on S1 equivariant homology, reduced one for me. So you do the following, you take two chains and well, you take a loop product of B alpha, B beta, as defined above, multiply them and push them with some sign, which I was also, we can write explicitly. So this is formula, well, I think originally due to Cohen and Jones, didn't appear in the paper of Chas and Sullivan. They defined this geometrically, but once you have a loop product, this is a perfectly well-defined bracket. And the theorem, well, of Chas and Sullivan, that this really makes S1 equivariant homology a gradedly algebra. With respect to this bracket. Okay, so now to state the theorem, I want to get to our main theorem. Let me introduce another very natural operation on loop space, on free loop space, which again classical, and in fact were defined even earlier than well, then this string operations. So let me call it, usually it goes under the name Frobenius or Hodge decomposition. Again, there are versions of this decomposition for homology of Lx, but I will restrict specifically to this S1 equivariant homology. So let me consider well, so these operations are coming simply from self-coverings of the circle in the following sense. So for any n, I can define, let's say, omega n natural maps from S1 to S1, maybe omega n here, which just sort of n-fold coverings of the circle by itself. So we have such an operations. So we may try to use this operation to induce well, operations on of course this give me naturally let me use some notation, give me naturally by simply pulling back maps on Lx, but these maps, strictly speaking, are not S1 equivariant. So literally, directly, they do not induce and graded endomorphism on S equivariant homology. But if we take this equivariant homology with rational coefficients, we can actually pass to rational spaces. So not S1 equivariant. But what we can do, we can actually localize. I will say about this in a moment quite a bit. We can localize this free loop space at rational numbers, or more precisely, I will take this Borel vibration and localize at rational numbers. I will explain what it means in a moment. I will try to explain everything what I mean. And then after localization, it turns out that these operations actually give me commutative diagram as wanted. And therefore, if I look at S1 equivariant homology with rational coefficients, or with coefficients in any field of characteristic 0, I do have graded endomorphism induced on these homology groups. Yes, so I should say that this construction originally, again, classical, goes back to topologists Burgilia, Fyodorovich, Gaida, I think in 90s, 90 something, 94. So we have natural maps. Let me denote it this way on this localized vibration sequences, and these maps do induce on equivariant homology, do induce graded endomorphisms, which we can use to look at, which we can use to construct a sort of eigenspace decomposition for this. So phi and tilde x give me graded endomorphisms. Let me, so n is fixed. In case if I use rational coefficients, right? So these are graded endomorphisms. So what I can do, I can consider common eigenspaces with eigenvalues n to the power p for every p greater or equal than 1 of this graded endomorphism. So defined. Yeah, of course. But for different ends. So what I will do, I will consider, okay, let me introduce another piece of notation, which I will later refer many, many times. So, so for p greater than 0, so I add this sort of Hodge power, Hodge index. So this will be, well, so what should I take? I want to take common eigenspaces of these graded endomorphisms. So I guess, how can I write it? Yeah, probably like this. With eigenvalues n to the power p. So now p is fixed. And we can look, so these are my eigenvalues. And we can look at such subspaces for every p. And then the theorem of Gaida, Burgilia, and Fyodorovich tells us that this S1 equivariant homology of Lx is, there is a natural direct sum decomposition of this form. So the natural inclusion actually assembled together and give us this direct sum decomposition. Well, summation starts with 0. Later there will be a shift, but so this is what goes under the name Hodge decomposition. or Frobenius-Hodge decomposition as they originally called it. And as I emphasize, whatever I am doing here is, well, essentially pure topology, well, rational topology, which is rational homotopy theory, but anyway, topological. So now we have two things, right? We have this string topology bracket, one thing, and the other thing, we have this direct sum decomposition. And the natural question is, well, are they compatible? Well, more precisely, well, does this bracket preserve this decomposition?
Behavior of the bracket with respect to multiplication.
Sorry, what?
What's the behavior of the bracket with respect to product? Is there, it's not like this.
I will answer this question. This will be my main question. Short answer, it's a non-commutative derived Poisson bracket, but derived. This is exactly the question I'm going to talk about. I'm just trying to give you from an angle, from geometric angle. It's remarkable that the statement is purely, so now let me, make a geometric, well, so to state a theorem, say one extra word. If you think of spaces rationally, forget about sort of torsion phenomena. I will say exactly what it means in a moment. Then it was discovered in, I think in 90s, that there is such kind of what they call rational dichotomy. Or dichotomy. So all rational homotopy types are divided more precisely. So if you take simply connected spaces of finite rational type, so every rational homology is finite dimensional. So they can be divided into two big classes, so-called rationally elliptic so these are the spaces. So all simply connected, one connected spaces of finite rational type can be divided into two classes called rationally elliptic. These are those for which, okay, so these are simply connected, there is no fundamental group. But if you take higher homotopy groups, rationalize them, so you get rational vector spaces and consider just the sum of all of them. So this has finite dimension. So all homotopy groups, rational homotopy groups, have total finite dimension. As vector spaces over Q. So this is a strong restriction, and what is called rationally hyperbolic. So these are those for which, if you look at these dimensions and cut at some n, so this numbers, so these numbers as functions of n grow exponentially. Of course, as you can guess, well, generic spaces are rationally hyperbolic, but I should say that there are many examples of rationally elliptic spaces. If you care about nice spaces, well, I actually have a list. Well, for example, like spheres, complex projective spaces, for example, all simply connected compactly groups, or all simply connected homogeneous spaces are all rationally elliptic. So many nice examples. And of course, this rationally elliptic spaces, it's a side remark, as I was reading recently. Actually, it's there is a famous conjecture in Riemannian geometry, which is attributed to Bott, who actually, the conjecture says that if you consider simply connected Riemannian manifold with constant sectional curvature, they must be rationally elliptic. There is a lot of work on this, but anyway, there are a lot of examples. And condition is very simple. You just take simply connected space, rationalize its homotopy groups, and consider this vector space if it has finite dimension. So it is. So the claim, so now the main theorem is the following, that oh, I cannot. The main theorem is that if I take this simply connected closed-oriented manifold and assume that as a topological space it has rational elliptic type, then this string topology bracket preserves Hodge decomposition. So theorem well, actually there was a bunch of conjectures, but okay. So assume that X as a topological space is rationally elliptic. So then, okay, let me say it maybe precisely. We have the following. So there will be some shift of degree, which will be explained in a moment later. Well, no, not in a moment, but later. So if I take Hodge pieces of degrees p and q, so this sits in H S1 p plus q minus, I guess, 1, right? For all pq greater than 0, p plus q greater than 1. So this means that this Chas-Sullivan-Lie algebra for simply connected spaces of rationally elliptic homotopy type is bigraded. So one gradient is just homological gradient, the other gradient is a Hodge gradient shifted by 1. Okay, now this is the first kind of half of my talk, and my second part will be, well, as I said, we will not try to prove this theorem directly. What we will do, we will carefully translate it into algebraic, more algebraic language, and this translation is based on, well, on Quillen's famous, okay, maybe I should erase this. Quillen's famous paper, Rational Homotopy Theory. It's a classical paper. I always recommend my graduate students to read it. It's, in my view, one of the best papers. Quillen was not expert in topology, but he wrote a paper which is every sentence is very clear and understood. So what did Quillen do? Very briefly, since well, so Quillen considered. Let me introduce some notation. So this one connected pointed spaces with pointed maps. So the one stands for one connected. One connected means simply connected. So he introduced what is called rational homotopy category. So rational homotopy category is defined in the following way. So you simply consider all maps between spaces which are rational equivalences. Right, so definition, if I have a map between two spaces in this category of pointed connected one connected pointed spaces, so it's rational equivalence if on all homotopy groups it induces isomorphism after rationalization. Very naturally. Of course, there are many other conditions which characterize this class of maps. One way or another, you select this class of maps, which are referred to as rational equivalences. And then you simply formally localize the category of one connected spaces, this category, at the class of these maps. Class of rational equivalences. And this is what he calls rational homotopy category. Of course, what he is simply saying that if you care about spaces, if you think about homotopy types only up to rationalization, you look at maps which have, say, torsion and cotorsion co-kernel on higher homotopy groups. So then you really can localize, and the main theorem is the following. So this category has a purely algebraic description, well, depending on the definition of algebra, but I think which says the following. So I want to say there are, you want to say there are natural equivalences of categories. So I don't want to use the word natural. So the first equivalence will consist actually of 7 functors, so which are quite clever. So there are equivalences of categories. Let me. So on one side, I have this rational homotopy category. Then I have a homotopy category of now purely algebraic object of differential graded Lie algebras over Q, sorry, which are reduced in the sense that these are chain de Lie algebras. So they're non-negatively graded, and in degree 0, you have 0. So this is what is called reduced. I will put 1 here. So reduced DGLAs. So there is a natural equivalence. And the other one, he also stated in this way, the other one is purely algebraic, of course, very well known nowadays, and goes under the name of Cajal duality. You have a differential graded co-commutative or algebras which are two reduced. So this means that component in degree of 1 is missing, is 0. So this is co-commutative DG co-algebras. He uses the word two reduced. Right? So this equivalence is actually, well, induced by a natural, maybe I should, yeah, so before going to algebra. So what does this theorem say? It says that once you have a rational homotopy type, a space X, to such a space, you have assigned a differential graded Lie algebra, which I will denote alpha X, right? And I also assign to differential graded algebra G, co-commutative co-algebra, which is easy to define. This is just a classical Chevalier-Lindbergh complex. I will denote it by C star. So this de Gilly algebra is called the Lie model, or Quillen-Lie model of X. And the theorem basically tells you that it encodes all information about topological space up to rational homotopy, well, in this one thing. So I should say that, of course, the homology of this Lie model, right, is just what is called homotopy Lie algebra of the space, or Whitehead algebra. So what you simply do, you take direct sum of all homotopy groups rationalized, or nice way to write it is the following. So usually it goes under the name Lx. So you take all homotopy groups of base loop space rationalized. And on this thing, you have a natural bracket, which is called Whitehead bracket. Which is simply comes from roughly from the group commutator on omega x as a topological monoid, topological group. So this is actually a graded Lie algebra. And so Quillen's model is simply refinement, kind of differential graded refinement of this classical object. So homology of this de Gilly algebra is homotopy Lie algebra. And of course, homology of this thing is just the homology of the space. With a natural coalgebra structure. Now, once you, okay, so once you know this, once you know this theorem, of course, you will try to rewrite, to express all, translate all topological objects, well, topological, yes, topological objects in the language of de Gilly algebras. And most important theorem for us is, again, classical theorem of, well, from 90s of Goodwillie and so theorem. So this is usually goes under the name Goodwillie and Jones. They prove it in. The theorems are the following, that if I take a space, simply connected space of finite rational type, to be precise, take the corresponding Lie model, take its universal envelope in algebra, and compute its Hochschild homology on one side, then what you, and I will care about reduced Hochschild homology. So you will recover exactly this reduced homology of free loop space. In fact, there is a natural isomorphism going like this. And if you take cyclic homology of this thing, right, then you recover, well, S1 equivariant homology of Lx. So now this, of course, explain, and of course, if you use this, I will refer to it, Goodwillie-Jones isomorphisms. I think usually it's denoted alpha and beta x. So under these isomorphisms, if you look at that Gisin sequence that I think probably erased already, yes, under this isomorphism, Gisin sequence becomes relating these groups becomes really cone periodicity sequence, exact sequence relating Hochschild and cyclic homology, right? So this is Gisin sequence identifies with cone periodicity sequence. So this is actually, well, sort of starting point for our translation, because, well, there are immediately two questions, question 1 and question 2. So question 1, well, what happens to string topology bracket on this side? on cyclic homology. That's question 1. And question 2, well, we need also algebraic model for this Hodge decomposition. So what does happen to Hodge decomposition? Okay, so, and I will try to answer this question one by one. Short answer to the first question is the string topology bracket. I think it's a remarkable coincidence. Well, the string topology bracket on reduced cyclic homology, yes, 4 minutes. Oh, you should have told me, okay. Anyway, I stated main theorem. Now let me link let me make it short. So answers. Well, let me appeal to Alexander Radesky talk. So he explained this remarkable bracket on a quotient of an algebra by span of commutators. Of course, people who know cyclic or Hochschild cyclic homology theory knows that this is can be interpreted either as Hochschild, or I want to interpret it as zero cyclic homology of an algebra, right? So this non-commutative Poisson bracket is actually a bracket on zero cyclic homology. What we need a kind of generalization of that structure that gives, well, graded Poisson bracket on the full cyclic homology. A graded Poisson structure on the full cyclic homology. And so this is non-commutative Poisson structure. In fact, I don't know if you refer to a paper of Crowley-Bowie, which I think you should have. Yeah, so he actually calls this very nicely. He's actually, in the preprint version, he called it non-commutative Poisson structure, but later he introduced this, he called it, if you look at the published version, he called it H0 Poisson structure, right? Poisson bracket. Sort of hinting that there must be a H star. And indeed, there is an H star, which there is a structure that induces this graded bracket on associative, well, differential graded associative algebra. So need graded Lie algebra structure on full cyclic homology. Okay, so my sort of theorem is, well, our theorem and construction that you can actually define the category of what we call non-commutative DG. So there exists a category which I will denote this way. So K is just any field of characteristic 0 of non-commutative DG Poisson algebras. That objects in this category is a DG algebra together with a bracket on let me try to give a careful definition. It's not long, but it's a very natural thing. So by this symbol, I denote slightly modified version of this. I will divide by K plus commutators. So this is what is called cyclic functor. So notice I do not restrict to free algebras. I'm just considering arbitrary differential graded algebras. So if you take a differential graded algebra, you can consider all graded derivations with usual commutator bracket, then you can consider subspace that I denote this way of all graded derivation which map A to this subspace. You can easily check that such derivations form a Lie ideal, differential ideal inside of this Lie algebra. And so what you can do, so this is the Lie ideal. And what you can do, you can consider a quotient algebra, quotient de Lie algebra of this graded derivation modulo Z ideal. So this has, of course, induced bracket, and then this de Lie algebra acts naturally on this quotient space simply by an action induced by derivation. So we have a natural action of this thing on, let me write it in the following way, a little bit formal. I have a de Lie algebra homomorphism like this, which is simply induced by the action of derivations on this space, right? Now, if I want, so now definition, this, okay. Anyway, so, right. Anyway, so you can define formally the notion of this non-commutative de Lie Poisson algebra. The main point is that this thing comes with two functors. One functor to the, okay, let's leave formulas. You all know how to write formulas. This is basically mimics definition of Crowley-Bowie in non-derived case. But the point is that this thing comes together with two functors, one on de Lie algebras, forgetful functor, and one on de Lie algebras. So so this gives me a Lie bracket on this space. And then I can define the notion of weak equivalence. This is a crucial thing. So I can consider maps of this de Lie Poisson algebras such that under these two forgetful functors, it induces weak equivalences of de Lie algebras and de Lie algebras. Then it turns out that this category with this class of weak equivalences, well, I want to say it's a model category. Unfortunately, we cannot prove it. But it has many nice properties. In particular, it's a saturated homotopic category, homotopic category. So it does have actually a very nice, well, well-behaved homotopy category. So when I'm talking about this, well, derived non-commutative derived Poisson algebra, this is simply pairs consisting of de Lie algebras together with a Lie bracket on this space satisfying certain extra condition, but viewed as an object in this homotopy category of de Lie PAK, right? So we introduced this a while ago, like in 2012, for purely algebraic reasons. But the point is that this is really, well, key objects for this. So main observations that the string topology bracket is an example of such a derived Poisson bracket. And I stop here. Thank you very much.
Time for some short questions.
Yes.
If A is a free algebra,